Lecture 25 covers section 7.9. Then today's lecture, you should be able to construct an integrator and differentiator circuit using op-amps. That is, we're going to go in a little greater detail about how these op-amps function. To begin, recall our expression for the output of a differentiator op-amp. Our output voltage, V out of t, is going to be equal to the time rate of change of our input voltage times the quantity minus RF, our follower resistance, times C, our capacitance. Now say we're given a differentiator op-amp where capacitance is equal to 0.2 microfarad and our follower resistance has a value of 5 kiloohms, and we have the following input voltage. V n of t is equal to 2000 t in between the times of 0 and 2 milliseconds. Then thereafter, it is equal to 8 minus 2000 t between the bounds of 2 and 4 milliseconds. We want to determine our output voltage given our input voltage at time t is equal to 0 is equal to 0. Now to do such, we have to construct an expression that relates our output voltage in terms of our input voltage, our capacitance, and resistance. Our output voltage is going to be equal to minus RF times C times the time rate of change of our input voltage. The quantity minus RF times C gives us a value of minus 0.001 seconds, and this is times the time rate of change of our input voltage. Now we have two time intervals that we have to be concerned about. The time rate of change of our input voltage between 0 and 2 milliseconds would be equal to 2000, and if we multiply this by minus 0.001 seconds, we'd have minus 2 volts. Now in our next time interval between 2 and 4 milliseconds, we'd have 8 minus 2000 t, which gives us the time rate of change of our input voltage being minus 2000, multiplied by minus 0.001 seconds gives us a value of 2 volts. We see our output voltage is going to alternate between minus 2 and 2 volts in every 2-second interval. That is, the derivative of a line of constant slope is going to be a constant value.